We have different sequences. These are the ones we're going to focus on. There's other sequences. We'll get to those. We are getting to those on our homework. But arithmetic, you go from one term to the next by adding 3. Geometric, you don't add the same amount, you multiply. So you would take 6 times 3 and 18 times 3. So you would multiply by 3 to get ensuing terms. So this is just geometric and this is arithmetic. Over here we have other things. What we discovered on our homework last night is this is 1 squared, 2 squared, 3 squared. So the pattern here is that the number of the term gets squared and that gives you what the actual term is. We'll be dealing with those later. We want to focus on these guys mostly in this unit. So, arithmetic, we said yesterday that we could make this, we could use this formula, either a sub n or u sub n, and we'd say let's take the first term, like 8 here, let's add the common difference, in this case 3, times n minus 1, and that would give us a formula for finding the nth term. But hopefully after that video we realized it's easier to come up with a rule that would say, you know what, let's go back to the 0th term. If this is u sub 1, let's go to u sub 0. If we add 3 going this way, we could subtract 3 going this way, and that would take us down to 5. And so we could start with like the 0th term and just add d times the number of terms we use. So to get to the 5th term, from the 0 term, we add 1, 2, 3, 4, 5. We make 5 jumps of a common difference. So just like that's the y-intercept and the slope or the rate of change is 3, we say, oh, y-intercept, slope is 3, we can get a formula real quickly. You should be comfortable using both approaches because it makes you a better problem solver, more powerful, more flexible, and whatever, so that you can handle things from any perspective. Now we're going here. Arithmetic is linear. It's like a slope, a rate of change, and a 0th term like a y-intercept. Geometric is exponential, because if we keep multiplying by 3, that means we're going to multiply by 3 to a power, like 3 to the n, to find the nth term. Well, once again we have a formula, and this time the formula might say, to find the nth term, start with the first term and multiply that by the common ratio. What do you keep multiplying by? In this case, keep multiplying by 3. The common ratio, which, I'm sorry, we need the general case, so that should be r. Over here it's a common difference. What we add together is the common difference. What we multiply each time is going to be the common ratio. So we'll take the first term times the common ratio and raise it to the n minus 1 power. This will give us a formula for finding the nth term. So in our case right here, the first term is 6. First term is 6. We're going to multiply it by the common ratio. We keep multiplying by 3. And by the way, the other way to find r, the common ratio, take a term like 54 and divide it by the term right before it, which is 18. That gives you 3. So you know that 54 is 3 times whatever 18 was. Same holds true for these guys. The common ratio can also be found by taking the 18 and dividing it by the term right before it, which is 6. That also gives you 3. So when you see that you keep multiplying by 3, that's the common ratio. That's the r that goes in this formula right here. So we have 6 times r raised to the n minus 1 power, and that would give you a formula for finding the nth term. So we can go ahead and use that. And if we wanted to find, let's say we wanted to find the 5th term, we could take the first term, multiply it by 3, raised to the 5 minus 1 power. 5 minus 1 is 4, so we'll multiply by the 3 4 times, which should make all the sense in the world. If you're going to the 5th term and you're starting at the first term, then here we are. Here's the first term. What does it take to get us to the 5th term? Well, to go from the 1st to the 5th term, we'd have to multiply by 3 to get to the 2nd term. Multiply by 3 again, that's the second time we multiply by 3. Multiply by 3 again, and then multiply by 3 one more time. It takes 4 jumps, 4 multiplications of 3 to go from the first term of 6 to the 5th term, u sub 5, which is going to be 3 times this, which would be 486. So to go from the first term to the fifth term, you would make 4 jumps. 5 minus 1 is 4. Now, let's do one more thing. Let's tie this together to what we did over here, because honestly, a lot of times, if they give you a formula for finding the nth term, they're not going to give it like this. They're not going to have it raised to the n minus 1. They're going to have it raised to the nth power, a lot like this over here. They're going to give you the formula this way because it's concise. They're not going to give you the formula starting with the first term and having n minus 1 jumps of the common difference. They're going to distribute it out and change it to this. They're really going to have you start with the imaginary 0th term and then add the common difference n times. So we're going to do a similar thing right here. Here's what we're going to do. This is the first term. But let's go back and see what the 0th term would be. If we keep multiplying by 3 to go this way, don't we divide by 3 to go this way? So to get back to the 0th term, we would divide the 6 by 3, and that would be 2. So it's a lot simpler for us to say, okay, the nth term would be to start with the y-intercept, the 0th term, which is 2, then just multiply by 3 to the n power. So this is a lot more concise. I would prefer to do it this way. It's easier. Well, it's arguably easier or not, but it's more concise and we can go that way with it. So just understand there's a subtle difference between this formula and this one. This one starts with u sub 1, this one starts with u sub 0. So this makes n minus 1 jumps, this makes n jumps. And it's a lot like this. This starts with u sub 0, makes n jumps. Starts with u sub 1 and makes n minus 1 jumps. In class, I want you guys to come up with rules in about 6 or 7 seconds, starting with the y-intercepts and going this way. Let's practice a little bit more. If we find the nth term, here's the formula. U sub 1 times r to the n minus 1, we got the common ratio. We can either use the formula, working from the first term, or we can problem solve and start with the y-intercept. So over here, if we use the formula, then we say, okay, here we go. The formula for the nth term is going to be start with the first term of 20, multiplied by the common ratio. Do we agree that 80 divided by 20 is 4? This divided by this is 4. So we know we keep multiplying by 4. That's why this is geometric. So our common ratio is 4, and we raise this to the n minus 1 power. That's sufficient. We can do that, and that works. If we wanted, okay, now let's go to this guy. Let's problem solve and find the 0th term. If this is the first, second, and third term, if we go back, instead of multiplying by 4 going that way, we divide by 4 going this way. 20 divided by 4 is 5. So the 0th term, the u sub 0 term, would be 5. So we can just start with the nth term, working off the 0th term, is multiplied by 4 to the n power. I would argue that this is a more concise approach. This tends to be, if they give you a rule, they're giving you that rule. They're not going to give you this rule. Either one is fine, but I'd rather you could come up with that, even in your head, much quicker than to toss this guy in here. So, how do we do this? We could say, okay, we got to find a formula and find the 8th term for this guy right here. Can you see what happens when we keep multiplying? What do we keep multiplying by? Hopefully you can see that we're multiplying by 1/3. That's why the denominator is getting bigger. It's as though this was 2 over 1, and we keep multiplying by 1/3 over and over again to get the subsequent terms. If you don't recognize that, then use the formula for r. Take a term like 2/9 and divide it by the term right before it, which is 2/3. When you divide by a fraction, you change to the inverse operation, which is multiplication, and multiply by the inverse of that fraction right there. And so the 2's will cancel. You'll get 3/9, which is 1/3. You have correctly identified the common ratio. So there's 2 ways to do this. U sub n equals u sub 1, which is 2, multiplied by the common ratio of 1/3, raised to the n minus 1 power. Or you can say, let's start with the 0th term. If this is the first term, then if we multiply by 1/3 to go this way, we multiply by 3 to go back this way, 0th term would be 6. We would just take 6 times 1/3 and raise it to the nth power. Either approach is fine. I'd love it if you could do this, because to change this to this is kind of complicated. You have to use negative exponents and whatever. But either rule works. Give you full credit for either one. Would love you to be diverse and be able to go more than one way. All right, take a look at this one. Is it geometric? If it's geometric, then if we take this term divided by its previous term and get 5, we better get the same ratio when we take this term and divide it by its previous term, which is also 5. So the common ratio R is 5. First term is 2/5, so the nth term would be 2/5 multiplied by the common ratio raised to the n minus 1 power. And if we wanted to find the sixth term, like that previous problem, I forgot to finish it off and say let's find the 8th term. What if we were going to find the 6th term in this one? Let's do 2/5. Let's multiply it by 5 raised to the 6 minus 1 power. So that would be 5 to the 5th power. So we'd say, okay, it'd be 2/5. 2/5 times 5 to the 5th power, which would be 2/5 times 3,125, because 625 times 5 anyway. So we get that answer there, and you can bust out the calculator. It'd actually be 625 times 2. We don't care, it'd be 1,250, but that's fine. The answer would be 1,250 would be your 6th term. Double check, but I'm pretty sure that's it. So here, Mr. and Mrs. Flubber, they're going to give birth to a bouncing baby boy. He bounces back to 80% of the previous height. Now, most of you are so young you haven't seen the movie Flubber, but it's just this green stuff that's alive and it bounces. It loves to bounce. So it's okay to bounce a baby Flubber. It is never okay to bounce a human baby. Okay, just make sure we got that clear. Now, we're going to drop this Flubber baby from a height of 12 feet, and it's going to keep bouncing back up to 80% of its previous height. Find the height after 5 bounces. Not a bad idea to visualize what's going on. Here's baby Flubber. Woohoo! Boing, boing, boing. It bounces back up to 80% of its previous height. So this height here would be 0.8 times 12. That's 9.6 feet. And then it bounces back again after that. So how high will it bounce after the nth bounce? Well, we could say it was dropped from a height of 12 feet. So the first term would be 12, and we'd multiply it by 0.8 raised to the n minus 1. Now here's the interesting thing. If we start with 12, the first bounce is right here at 9.6. So to get to the 5th bounce, this, you guys, is actually like u sub 0. This would be as if there was a bounce that took us to the 12-foot height. So what's nice about this is we can use the simpler approach. This 12-foot height is like u sub 0, and now, how do you find the height after the 5th bounce? That's this height right here. So we have to drop it and then bounce once, twice, 3, 4, 5 times. That's why this is really u sub 0, as if there was a bounce that took us up to here. So we're just going to multiply this times r raised to the n. So there's our formula right there. Now, if we were going to use the formula that said you've got to use the first term in the sequence and then multiply that by 8 and do that to the n minus 1, then actually the first bounce in the sequence would be 0.8 times 12. That would be 9.6. And we need to make this guy 9.6 and then 0.8 to the n minus 1. So this works if you use the formula. This works if you use them kidneys. If you just realize that's like the 0th bounce, a bounce that took us to that height. Then when we dropped it, we got the first bounce, the second bounce, the third bounce. Either one of these two things is legit. We want the height after the 5th bounce. I would tend to go there. I think that's easier. You put a 5 in there. You take 0.8 to the 5th power and multiply it by 12. And that will give you your answer right there. I think that's, yeah. So 0.0004096 times that, but we don't care. Just bust out the calculator and you can do it. Just say that your height after the 5th bounce is 12 times 0.8 raised to the 5th power. So you're going to do that in your calculator, and that will be this height right here, the height after the 5th bounce. So geometric, if we multiply by a common ratio, you're going to find your formulas by either using this guy, u sub n equals this, or by going back to the 0th term and doing it a little bit more practically that way. And so that is the introduction to the geometric sequence.